At this point, I'm going to assume you're familiar with the classification scheme of sedimentary rocks and the names of some of the most common ones. But I especially want you to distinguish between the sedimentary rocks that are made from calcite and those that are composed mainly of silica. Chalk, calcite, diatomaceous earth made of silica, just as an example. So how would we determine the difference between the two? The good friend that we have, the good old acid test. Anything made of calcite will fizz, anything made of silica will not. Remember, silica is mainly quartz. So let's go on to sedimentary structures. Let me hide these controls. So sedimentary structures are very important because they give geologists a way to look into the Earth's past. They're clues. One of the more obvious clues is the bedding of sedimentary rocks. Sedimentary rocks are characterized by the fact that they form in layers. When sediments are deposited, they are normally, in most cases, horizontal. If we see anything that's tilted, then we know that that happened after those rocks were formed. So we call those layers strata. Strata is Latin for layer. So layers of sedimentary rocks that have a recognizable top and bottom. Those layers represent a particular depositional episode in Earth's history, and they can be thick, they can be thin, they can be interbedded, thick with thin, layer after layer after layer of different sizes. A formation is a strata that can be traced over a very large region. Some formations can go for hundreds of miles. So if you think about what this means, it means that that was a very large depositional environment. Sedimentary facies are rhythmic bedding, and we'll look at what that means when we get into transgression and regression. Special kinds of bedding are those beds that tilt at an angle. Crossbedding, very common in sandstone. If things are cross-bedded, if layers are cross-bedded, that means that wind or water played a role in the placement of those sediments. Graded bedding is where the particles fall out according to size. So you'll have large particles on the bottom, and as we go up the strata, the particles will get smaller and smaller and smaller. And we'll look at what causes that to happen. Bed surface markings are another clue to past ages. There can be ripple marks like we see today at a beach or in a river. We can determine the type of wave action that was going on, the speed of the current when we look at these ripple marks, depending on what their characteristics are. Mud cracks, anytime we see mud cracks, or fossilized mud cracks, I should say, they indicate alternating wetting and drying conditions. There had to be mud, so that means that the sediments had to get wet. And then for the cracks to form, the sediments had to dry out. Fossils are also indicative, or not indicative, but they are abundant in sedimentary rock layers. Because normally organisms are abundant where sediment accumulates. Then bioturbation, these are other markings that are left over in sedimentary rocks. Bio meaning life, turbation means that those sediments were disturbed in some way. So for example, there might be tracks of animals left over in the mud, or there could be marks from where worms have burrowed into the sediments, and then those become fossilized. So sedimentary facies is any aspect of a sedimentary rock unit that differentiates it from an adjacent sedimentary rock of a similar age. That can happen as a result of changes in river velocity or movement of rivers, but one of the more common ways that it can happen is where we have ocean levels rising and falling. We call that marine transgression if the sea level is rising, and we call that marine regression if sea level is dropping. So if sea level rises, then we will see a certain sequence of rocks. And by seeing a certain sequence of rocks, where might that be? Well, maybe in a road cut. But more commonly, it's where geologists have gone out with drills and they pull up rock cores from miles deep inside the earth. And looking at the layering of rocks and the type of rocks that show up in that core from the bottom to the top, we can determine whether sea level has risen or fallen. What kind of environment was it like, millions of years ago, to see these particular rock types that we're seeing in the core? So for example, marine transgression, we might have from bottom to the top, we would have sandstone, shale, and limestone. Sandstone would represent a beach environment. Shale would represent a shallow marine environment offshore of a beach maybe, and limestone would be deeper ocean. So from bottom to top, if that's the sequence, that means that sea level had to be rising in that order. Marine regression, on the other hand, is withdrawal of the sea from coastal area, a drop in sea level. So from bottom to top, we would have limestone representing the ocean being there at one time, then the shale, shallow marine environment, and then the sandstone, the beach environment. So land is emerging in that particular case. This, if we look at this first picture right here, we see sea level at a particular level, and the rocks that we would find from deeper ocean to beach would be limestone, shale, and sandstone. Then if sea level rises, what happens is the sand is going to be deposited further inland. There's going to be mud deposits or shale that would be deposited on top of the sand, and then the limestone would be deposited on top of the shale itself. Then sea level rises once more, and we drill a core into the rocks and drag them up, and we find that the sequence from the bottom to the top is sandstone, shale, and limestone. This is indicating that, let me get a pencil here, a pen. Let's choose a color, let's do purple. Okay, so we see that here's the sandstone here, here's the shale, here's the limestone. So that indicates that sea level has risen if we have a core that shows this particular sequence of rocks. And let's say something really crazy happened and there's coal on top of the limestone. Well, coal is from a swampy environment. So we might have rocks that are missing here, but from that limestone to that coal, we know that environmental conditions changed drastically. We're on land once more, so the ocean regressed. Okay, let's look at this other side here. Okay, so here's where the ocean level is to begin with, right here. There's our sandstone, our shale, and our limestone, deep ocean, shallow marine, beach environment. And then sea level begins to drop. So our sand is going to be being deposited further out now. Then we have the shale, then we have the limestone, and then it drops even more. All right, let's drill a core. There it is. We pull the rocks up, and from the bottom of the core to the top, we would find limestone on the bottom, shale, and then sandstone. So that indicates that sea level has been dropping. And then let's say, okay, we've got limestone on top of the sandstone. That means that deep ocean came back. And we find that we can look at many different rock sequences. This one happens to be a road cut in Utah. And this whole thing right here is just representative of sea level rise and fall. We have limestone interbedded with sandstone, interbedded with shale, and then the sequence starts all over again. Crossbedding, or where layers are arranged at an angle to the surface where they were deposited. We see sand dunes like this on the beach, in deserts. Sand is mobile, so sand moves as the wind blows over it. And it can be from the Crossbedding can happen as a result of wind or water. So this is what we're looking at. These are some sand dunes. Sand dunes are just totally movable because as the wind moves up and over, then sand moves up and over. So over time, sand dunes are moved by the wind. This is crossbedding. And in rocks, we can see sand dunes superimposed, fossilized sand dunes superimposed upon each other, like this. This is in Zion National Park. All this is sandstone. We can see the direction that the wind was moving. We can see how it changes over time. You see how some of the sand dunes, if we're looking through here, some of the sand dunes were truncated over time, meaning cut off. Through here, we see the same thing. These are beautiful cross beds right here. And there's a bigger picture of it, just layer after layer, representing millions of years of movement of sand dunes, crossbedding. Here's another example. You see these lines here where things were cut off. Let's see if I look at, I can't draw straight with this, but look at those. Perfect. So there's the wind direction coming from this direction at one time. And then I don't see any in here showing change. Then graded bedding, an upward decrease in grain size. Graded bedding happens several reasons, but one of the main reasons is from turbidity currents. Turbidity currents, turbid, when water is turbid, it's dirty. It's full of sediment. So turbidity currents are these deep ocean currents that flow down a continental slope area just chock full of sediments. And when they come to the flatter area, then the larger size material will drop out first. And then in the sequence, smaller and smaller and smaller particles will be dropped out. So we call that graded bedding because the particles are graded in accordance with the size. And we can see that on seafloors as well as on lake floors. So here's continental shelf area right here. Let me get my pen back. Sorry, I'm still getting used to all this. Did I get it? Okay. So here's continental shelf area, ending right there. Then there's this break and we have a slope area. So think of all the rivers and streams carrying all these sediments offshore, accumulating up here. At some point they get, this gets overloaded, and under gravity, all these sediments are going to flow downhill, down the slope. And then they will come to a rest when the gradient becomes less steep. So the heavier stuff would drop out first, and then the lighter weight stuff. And in a rock sequence, well, here's not the rock sequence itself, but a cartoon showing that. The heavier things down here, lighter things, lighter weight material at the top. So that's a graded bed. And this is a graded bed in real life. The heavier material at the bottom, and then the lighter material at the top. And that in certain rock sequences, we can see indications of many turbidity currents. There is a great formation at the lighthouse at Point Reyes, a textbook example of deposition through turbidity currents, and not just one, but many. Here we go. Since I can't take you there, here's the picture. So notice how we have smaller material here, then heavier material, then smaller material. So this is just a sequence of turbidity currents that occurred. Look at the size of these particles in here. There's some of them that are almost as big. Okay, I'm exaggerating a little bit, but half as big as this little house right here. As you walk on down the sidewalk past this, big, huge chunks of granite. Oops, get back. That's the world famous Point Reyes conglomerate. Then ripple marks, small ridges with intervening troughs. So we have a crest and a trough. in sand, often in layers of sand, some in mud. Stream currents will form ripple marks, and the symmetry will show the direction of the current. Wave-formed ripple marks can be symmetrical from wave motion. So like this, ripple marks will form. Here's the current, direction of the current. So these are the ripple marks indicating the flow has been in one direction. Flow is from the right to the left here, so this way. And then when we have ripple marks like this, it indicates this to and fro motion of waves in shallow water. So these are some symmetrical ripple marks. And you can see how perfect they are. And they're in rocks, so those are fossilized ripple marks. Here we see some too. There, look at those. Those are pretty symmetrical. Then mud cracks in clay-rich sediments. Sediments deposited in an environment where there's periodic wetting and drying. So that could be on floodplains of rivers, on lake shores, or along the coast, or in tidal flats. So here are present-day mud cracks, very common. We see these a lot. And those are fossilized mud cracks. Then fossils, of course, evidence of prehistoric life. We can have body fossils, the actual remains of the organism, or trace fossils, which are tracks and trails that the organisms left behind, most often found in sedimentary rocks. There are some exceptions to that, but for the most part, sedimentary rocks are the ones that we're going to find the most abundant fossils in. Coral fossils will be deposited in the ocean. And then there's an entire branch of paleontology and geology called taphonomy, and that's the study of everything that happened to an organism after it died. Did it get caught in a flood and get washed somewhere else, or was there evidence of other animals feeding on it? You know, all the things, all the possibilities of the things that could happen to something after it died. So here's sedimentary rocks. I love this. This is from the Green River Formation in Wyoming. If you ever see these fish fossils, it's a pretty good bet that they come from that particular formation. But look at this. Perfect. You see the eye of the fish. You also see it gorging on another fish. That must have been a rude awakening for it. It thought it was having supper, and then all of a sudden both of them died. So paleontologists are getting so good with some of the equipment that they use that they can determine what color this fish was by the mineral content that they find in the fossil itself. So it's a pretty interesting science. So one of the major things then with sedimentary rocks is that we're looking at depositional environments. What was the earth like at the time these sediments were deposited? So we look at the clues in the rocks, the texture of the rock, the sedimentary structures that are located in the rock, fossils, of course, and features of ancient rocks as compared with rocks that form today. So uniformitarianism tells us that the same processes that were going on 1 billion years ago are some of the same processes that are going on today. So when we have clues to what is going on presently and we see things like that in rocks that are way old, then we know what sorts of activities were happening at the time to make the same rocks that we would see, or the same sediments that we would see being deposited today. And thank you, and I'll see you next time.